Okay, great. Everyone can hear me, I assume?
Yeah.
Right. So I promised dark matter, I promised the Large Hadron Collider, but I really have to start with Vera Rubin and some space. So what you discovered when you looked out was that galaxies were rotating in a way that we didn't expect. In fact, the way they were rotating, it was clear that there was far more mass, more matter in the galaxies than what we were actually observing. But that was really the only indication of the mass in the galaxies. And so that was really strange. And so, of course, you look into it, and you look into it to clear it up. And as we all know in science, what actually happens is you find more mysteries, right? So really what we found was that 95% of the universe is this strange, exotic dark matter and dark energy. And what we think of as normal, it's everyday, everything that we know and love and can never be and can never want to be, is in that 5%. We're the weirdos. But the thing about that 5% is that we know it very well. We know it's something called the Standard Model. And I don't want to get into a whole bunch of details about it, but really what it is a theory that describes particles and their interactions. And it's a very successful theory. In fact, predicting particles and some of their properties. Two of the particles that I really want to talk about for this story are the W and the Z. Now, what's special about them? Well, in a naive sense, in a naive understanding of the Standard Model, these particles should be completely massless. However, if you really look at the theory, you look at other areas of theory, there are indications, very strong ones, that they should in fact have mass. And of course, it turns out that they do. And they are on the order of 10 to the negative 25th kilograms. I have the physicist units up there, so no one complains about them. And that may seem like it's really light, but for the particles that you're familiar with, you know, the friendly proton and the electron, well, those are orders of magnitude lighter than the W and the Z. So while it solves one problem, if they have a mass, it doesn't solve the problem of the fact that they have mass. So how do you go about solving this problem? Well, it turns out that if you add something called the Higgs boson and its associated interaction, you can do some mathematical wizardry, which if you're inclined to do so, I suggest you look it up because it absolutely is beautiful, that has the mass of the W and the Z just pop out. And so that's great. And so now we're presented with a new problem. You got to find this new Higgs boson, right? Well, that's why this plot here is so important. This bump, this is probably the most famous bump in modern history. Outside of Beyonce's baby bump. We won't go there. So what this bump tells us that the Higgs is there. What the dips below tells us that we're really sure the Higgs is there. And what that guy getting the Nobel Prize means, yeah, it was important. And so now you're saying, okay, great, but what does it have to do with your work, your dark matter search? Okay, well, let's take a look back at the Standard Model and the Higgs boson, right? Well, with this new Higgs boson, we get a new interaction. And this new interaction might be able to interact with dark matter. Now, the thing is, some of you have probably noticed there's a little asterisk beside the. That's because I'm telling a little bit of a fib, that mathematical magic, that doesn't only predict one Higgs boson. It could just be one Higgs boson, but it doesn't limit it to that. There could be multiple Higgs bosons and multiple Higgs interactions, which gives us even more ways to interact, possibly, with dark matter. So how do we do this? Well, we would do this at a particle collider. So what we do is we take particles and we accelerate them at each other, and if our aim is good, sometimes they interact. Batman fans? And so when they interact, they might create a Higgs boson, rarely. The Higgs boson will then, in our theory, possibly decay to dark matter. And this dark matter might decay to normal matter, that 5%. Now this normal matter, it might be able to be detected by our detector. And when we actually interact with the detector, we get information from the event that we can use to reconstruct what has happened. Now, where do we do all this stuff? We do it at particle detectors like this one. This is CMS. It is located at the CERN Large Hadron Collider. It is on the border of Switzerland and France. Actually, it's 100 meters below the borders of Switzerland and France, and a big ring that runs around the ground. It's fantastic. And here's another view of CMS. And it's the best one on that ring. It's mine. And this detector is 14,000 metric tons. And remember, we're looking for particles that are on the order of 10 to the negative 25th kilograms. When it's powered up and when its magnets are on, it has the energy stored in them equivalent to a 747 in flight. And if you want to know the size of this thing, that's a person. And this is the Compact experiment. Now, this detector is really a bunch of sensors located around one central point where we collide protons. or other particles if you're in the heavy ion community. And when the particles come out and they interact with these sensors, we create events that look like this. Now, some of these events might possibly be what we're looking for. But they're very rare, so we need a lot of them. We collide protons every 25 nanoseconds, meaning we get up to 40 million events per second. Now, that is a lot of events to comb through. And have we found anything yet? Well, if you're familiar with the movie that I'm referencing, you know what I'm going to say. No, we have not found anything. But even not finding anything leads to new knowledge and new information. Now, this plot right here, yes, there's a lot going on, it's very complicated, but don't look at it like a plot. Look at it instead like a map that's been given to us by theorists. This is a map of possible configurations of the universe, although really it's a subset of possible configurations of the universe. And everywhere there's color, those are places we've already looked. But everywhere there's white, we haven't explored yet. We don't know what's there. There'll be dragons there. Right? And that's incredible when you think about it, because maybe we'll find some signal there. And that means we'll have a new way of looking at our universe, a new way of exploring the world around us. But maybe we'll find nothing. And if we find nothing, we'll have to come up with entirely new schemes, thoughts that no one has ever thought before. And I think that's incredible. And that's why we do this.